All right, last property of the year. We started way back in September with a specific volume, and our last property is for moist air. It's dew point, so dew point of moist air. Um, should have a psych chart for this so that you can look at your own psych chart and calculate or take some dew points off it. So make sure you got that. And let's just start by talking about dew formation. So it's easy enough to demonstrate it for yourself. I just did this myself. I got a glass of ice water. When I brought it into the room, the sides were completely clear of any sort of any dew. And then in about 5 minutes or so, we got a fair amount of dew, a fair amount of moisture on that glass. And of course, what's happening is that the air that's right here, that's next to that glass, it has moisture in it, and some of that moisture condenses on that cool surface. It goes from vapor to liquid and sticks there. All right, so what we want to do is think about what that process looks like on the psych chart. But first, just quick reminder, the moisture carrying capacity of air depends on its temperature. The higher temperature some areas, the more moisture it can carry. And of course, the converse is true. The lower the temperature, the less moisture it can carry. So you can probably put it together and get what's happening when you have some sample of air and you get moisture condensing out of it. It's cooling, and then it can't hold all that moisture it has. And so if it becomes in contact with a cool surface, then you get condensation on that cool surface. And that's exactly what happened with my ice water right here, is we got condensation on that cool surface. Okay, so what does that look like on the psych chart? So what you want to do is just imagine some sample of air that is not saturated, and then it ends up cooling, and that's exactly what happened. The air that's next to that glass started out maybe like 73, 74 in my room here, and then the air right next to the glass cooled, and eventually we got condensation. So cooling on the psych chart, remember the x-axis is our temperature, so cooling would be a process where we go to the left on the psych chart. That's what it would look like. But what about moisture? So I had this air and it was cooling, and when it's cooling before the moisture starts condensing, it's cooling with neither moisture addition nor removal. So what I just want to imagine for yourself is that if we started it with some air at some point on this chart, what would that process look like? Okay, we're going to go to the left, but there's no moisture addition or removal until dew formation begins, or until condensation begins. So that would mean constant moisture level. That means we would just be going directly to the left, and the air is getting cooler, cooler, and cooler. And then at this point, it gets saturated. The moisture in it is the maximum amount of moisture it can hold, and that's when condensation begins. So something that we're very interested in some cases for certain sample of air is, what is its dew point? If we cool that air, at what temperature would condensation begin? I've mentioned before that I do some HVAC work, and a lot of times we worry about that with pipes going through buildings. There's this air in this building, and if that pipe carries cold water, will that cold water pipe be able to condense moisture in that air? And so the way the question's usually put is, hey, what is the dew point of that air? So for any sample of air, to figure out its dew point, plot it on the psych chart, and then imagine a process where it's cooled without moisture addition or removal, and when you hit the saturation curve right there, you've reached the point of dew formation. Then you just read straight down and get what the dry bulb temperature is at that point, and that is called the dew point temperature. So repeat again, a last process. If you have some air and you want to figure out its dew point, plot that air on the psych chart, and then just draw a horizontal line until you hit the saturation curve. That's where dew begins, and you're going to read that temperature. And one way you can do it is go right down there and get the dry bulb temperature. But as you'll see when we do an example, there are actually temperatures on that saturation curve that match exactly with the temperatures down below on the dry bulb temperature. So you can just read the temperature off the saturation curve. All right, let's go ahead and get to work on that. We're going to do 3 quick examples. I encourage you to go ahead and plot it on the chart, and then take that line to the left and come up with a dew point. So first one, some Sacramento air during the summer. Let's make it 100 degrees Fahrenheit, and specific humidity ratio of 0.010. So go ahead and plot that point, 100 degrees Fahrenheit, 0.010. My chart's getting marked up a little bit, as yours will too, but that is that point that that large dot that I put up there is my initial point, 100 degrees, 0.010, and I'm wondering what its dew point. So I can just take that chart and just kind of eyeball it by going to the left and seeing where I hit that saturation curve. I'm going to go ahead and draw on the line to get it so I can see it a little bit more precisely. So I'm following, going to the left, staying on that W is equal to 0.010 line. Okay, following to the left. And that represents the process of cooling. Okay, so my picture's a little bit messy, but I went to the left, and I hit that curve right there. And now we're wondering, hey, what is that temperature? So you might be looking at that point right there and say, oh, it's between 55 and 60. Looks like about halfway. I'll call it 57.5. But once again, we want you to be more precise than that. And if you get good reading the psych chart, you will see that you're able to get finer temperatures than 55 and 60. And the way to do that is if you look at the chart where your dot is, okay, right over there, between 55 and 60, you can see these dotted lines that come off the chart there. There's a dotted line that goes down at 55. There's a dotted line next to it, another dotted line, another dotted line, another dotted line, and there's a dotted line at 60. They even, okay, have 55 and 60 on there. You've got 55 and 60 on there, but they have every line in between. They have the 56 line, the 57 line, etc. So what you want to do is find the nearest dotted line. And I'm going to look at my chart for just a second, and I encourage you to do the same. See where it is. Okay, and to me, it looks like it's right around that 57 dotted line. So we would say for our first example, our dew point was 57 degrees. I'm going to actually write that up on the top of my paper so we can refer to it later on. So what that would mean is that Sacramento air, during the summer, 100 degrees, 0.010, if you were going to get condensation on it with it, it would have to come into contact with a 57 degree Fahrenheit surface, and that air would have to cool to about 57 degrees Fahrenheit, or even a surface lower than 57 degrees Fahrenheit. Well, that's pretty rare outdoors during the summer, so we don't see condensation very much during the summer. Okay, next example. Let's do 95 degrees Fahrenheit and 0.017. So now we're in Atlanta, Georgia, or someplace like that, where it's hot, not as hot as Sacramento, but really humid. 95, 0.017, plot the point, find the dew point. Okay, I made a mistake on my first plot, but now I've got it. So I'm putting an arrow between the correct one, 95 degrees, 0.017, and then I'm just going to go to the left and just ballparking it, going to the left when I hit the saturation curve. It looks between 70 and 75, but we want to be more precise than that. So you don't have to do it. You can just follow the line with your finger to the left, but I'm going to do it myself. Go all the way to the left. Okay, so I got some Atlanta, Georgia, or Washington, D.C. air, someplace humid, hot and humid. It goes to the left. It's cooling, cooling, cooling. No condensation. When it reached this point, we would start to get condensation, and so we want to be more precise on what that is. So once again, we got to look at those dotted lines that are coming off there, and we can see that there's the 70, the 71 line. 72 looks right about where my dot is. 73. 74, 75. And I think that if you called it 72, that would be good enough. But it looks like it's slightly over than me. 72, 72.1 degrees is my second one. Okay, so dew point is 72.1. The way we visualize that is that air has a higher dew point. It does not need to cool as much in order for condensation to begin. Condensation is much more likely, and of course that's true if you're in a climate like that. You get condensing a lot more likely because the air has a lot more moisture. Okay, let's do the last one. Pretty cool evening. you're in your car, but you run the heat a bit, so it's pretty warm in there, 75 degrees Fahrenheit. You got a couple passengers in there, so the humidity level starts rising. Let's say it's in the car at 75 degrees, and the specific humidity is 0.010. So last example, 75 degrees, 0.010. Last example of the semester. Okay, so there's that dot, excuse me, right there is my 75 degrees, 0.010, and we would just follow it to the left, and we're going to go back to the same dot that we did for the first example. We follow it over, and it looks like that the dew point is about 57 degrees. Okay, so first of all, what does that mean physically? Well, you know, a lot of times if you're in the winter in a car, the glass itself gets really cool because it's cold outside. It's gonna be less than 57 degrees, so you're gonna get a lot of dew formation on glass when you're in a car. And of course, I'm sure you've experienced that. The second thing to observe is the dew point was the same for both the first example and the last example. And what was the same about the first example and the last example? Well, in both cases, they had the same moisture level. They had this moisture level of 0.010. Turns out that moisture level, or our specific humidity, entirely determines what dew point is. Okay, good enough. That is it. Last property of the semester. Just a note, there are a couple other properties on the psych chart. Those dotted lines that we referred to that cut through the temperature lines, like that dotted line you see there with the 75, those have a name, and those are called wet bulb temperature, and we're not going to do that this semester. You're not responsible for that. There are also some other diagonal lines that go through the chart, and if you take a look at the upper right-hand corner, there's one that says volume, cubic feet per pound mass dry air, and that's called specific volume. And again, we're not going to worry about that. We're just doing the properties that we've done so far. If you look through section 14.5, don't worry about wet bulb, and don't worry about specific volume. Okay, so keep working on homework number 11. Get that done. Please email with me any questions. I should send an email out as we get back to the end of the day on Sunday with reminder instructions about the test. And finally, I have one more solution set to post on SACCT, and I'll be doing that over the weekend. Good luck, and let me know if you have any questions.